Without mathematics, there is nothing you can do. Everything around you is mathematics. Everything around you is numbers. Hello everyone. Welcome to the third module of Introduction to Group Theory. Myself, Navya Joy, Assistant Professor, Department of Science, the Bhopal School of Social Sciences. In this session, we are going to learn about the order of a group, order of an element of a group, subgroup and examples of subgroup. In last two modules, we have gone through the definition of group and examples and its properties of groups. So what is the order of a group? The order of a group is its cardinality. What do you mean by cardinality? That is the number of its elements. The order of group is denoted by ORD of G or modulus of G. In last two modules, you have gone through various examples of groups. Some of them were set of integers with respect to addition, set of rational numbers with respect to addition, set of real numbers with respect to addition, set of non-zero rational numbers with respect to multiplication, set of non-zero real numbers with respect to multiplication. All these are examples of infinite groups. Why so? Because we know that the set of integers, the set of rational numbers, the set of real numbers, the set of non-zero rational numbers and the set of non-zero real numbers contains infinite numbers in it. That is why these are the examples of infinite groups. Now, what about the examples of finite groups? Some of the examples of finite groups are, first one is symmetric group. It is denoted by Sn. Symmetric group. What is its order? Its order is n factorial. Now, the second group is Dn, that is dihedral group. Dihedral group. What are its orders? The order is defined as 2n. And the third group is Q4, which is called quaternion group. Quaternion group. What is its order? Its order is 8. These are some of the very familiar finite groups. Now, we have seen about the order of a group. Now, what about the order of the elements inside the group? So, the next heading is order of an element of a group. The order, sometimes it is also called as period, of an element A of a group is the smallest positive integer n such that A raised to n is equal to E. This is the important condition which should be satisfied by the element A to have an order n. And what is E here? Here E denotes the identity element of the group G. And what do you mean by A raised to n? Here A raised to n denotes the product of n copies of A. Let us consider some examples. Okay, let G be my group and let the identity element be 1. And let us take the element of the group B minus 1. A equal to minus 1 be an element of this particular group G. So, what can be the order? What can be the order of this particular element? What can be the order of particular element? Minus 1. So, what are we supposed to check? We are supposed to check this condition. Here A raised to n equal to E is the condition. I can replace A by minus 1 raised to n. E is what? E is 1 here. So, I know that minus 1 raised to the power 2 is 1. Minus 1 raised to the power 4 is also 1. Minus 1 raised to the power 6 is also 1. Minus 1 raised to the power 8 is also 1. So, which is my n here? There you should focus. See, I have written here n is the smallest positive integer. So, which is the smallest positive integer here? I have 2, 4, 6 and 8. Obviously it will be 2. So here the order of -1 is what? 2, since 2 is the least positive integer which is satisfying this particular condition. Now what if the order of an element, let me consider it as 1. What will happen then? What can be the order of 1 here? I know that 1 raised to the power 1 is 1, 1 raised to the power 2 is 1, 1 raised to the power 3 is also 1. So which is the least positive number which is satisfying the condition a raised to n equal to e? Yes, it is 1. So here the order of element 1 will be 1. So this is all about the order of an element of a group with respect to the operation multiplication. Here always remember that we have talked about multiplication here. The second point is, if the composition in group G is addition. So in the last case we have talked about group with respect to multiplication. So what if the group is with respect to the binary operation addition? So we know that in most cases of addition the identity element will be what? The identity element will be 0. So let me take any random number, let me take the element 0 itself. So how many times should I add 0 to get 0? Even if 0 is equal to 0, 0 plus 0 is equal to 0, 0 plus 0 plus 0 is also even if giving me 0. So which case should I consider? I should consider the least positive case. So what is my condition here? My condition is NA equal to E. The least positive integer n will be the order of my element. So here my order of 0 will be what? It will be 1 here, since 1 into 0 is equal to 0. Now what if no such n exists? In such cases A is said to have infinite order and all elements of finite groups will have finite orders. So that is all about order of an element of a group. Now let us see some of the examples. The first example is the set of integers with respect to addition. So we know that what is the identity element here? Obviously the identity element will be 0. Now what element can I choose? I can choose my element as 0. Let me take first as element 0. So order of 0 will be what? We have already seen it will be equal to 1. Now what if my element is 1? Can adding 1 any times will give me answer 0? Is it possible? No, it is not possible. Adding 1 will not give you answer 0. So the order of 1 will be equal to what? Will be equal to infinity. And not only 1, therefore all the elements of integers except 0 is having the order infinite. You can also write order of A is equal to infinity if A belongs to Z minus 0. Except 0, all the elements in the set of integers have the order infinite. Now moving into the second example, that is the set of non-zero rational numbers with respect to multiplication. So what does the non-zero rational numbers contains? It contains all the elements of the form p by q where q is not equal to 0 and it is also excluding 0. So let me consider any rational number. Let my number be equal to 1. And what is the identity element here? Here the identity element will be 1. So what will be the order of 1 here? It will be 1 here. Now what about the order of minus 1 here? I know that 1 raised to 2 minus 1 raised to 2 will give me answer 1 and also minus 1 raised to the power 4 will give me answer 1. But since 2 is the least positive integer which is satisfying the condition, my element will be having order 2. These are some of the cases where I can get finite orders. All the other numbers except 1 and minus 1 will have infinite orders in the particular case of set of rational numbers here. Now my third example is the set of integers of modulo 6. So, I know that the set of integers of modulo 6 contains the element 0, 1, 2, 3, 4 and 5. So, let me consider any random number from here. Let my a is equal to 4, and I know that the identity element here will be what? Will be 0. So, how will the modulo addition works here? 4 plus modulo 4 will give me what? It will give me answer 8 modulo 6. And what is its answer? The answer will be 2. It is not equal to 0. So, the order of 4 will not be equal to 2. Now, 4 plus 4 plus 4 is giving me answer 12. 12 modulo 6 is giving me answer 0. So, what can I say? I can say that order of 4 is equal to 3, as it is satisfying which condition? As it is satisfying the condition of a raised to n equal to e. So, these are some of the examples of order of an element of a group. Now, moving into the next heading, that is subgroup. What is a subgroup? A subset H of a group G is called subgroup of G if H forms a group with respect to the binary operation in G. So, basically I can say the subset H is said to be a subgroup if it itself is what? A group. So, when I say H star is forming group, what all axiom it should satisfy? The very first axiom it should satisfy is closure axiom. What does it says? It says that if, let me take any two elements from my set G, A star B should again be included in the set H. That is, on applying the operation, binary operation star, the element should be contained in the same set G. That is what closure axiom says. For all A comma B belongs to H, it should be satisfied. Now, what is the next axiom? That is associative property. Associative property. What does it says? It says that if I consider any three elements from the set of H, then A star B star C should be equal to A star B star C for all A comma B comma C belonging to the same set H. No. What is my third property? Third property is existence of identity. What does it says? It says they should exist an identity element E which should belongs to the set H, such that A star E should be equal to E star A, should give me answer A. For all A belongs to G, the case should be satisfied. Sorry, H, it should be satisfied. Now, which is my fourth property? The fourth property is existence of inverse. Existence of inverse. What does it says? It says for all A belongs to H, there should exist A inverse belonging to same set H, such that A star A inverse should be equal to A inverse star A, which should give me the answer as identity element. Here my E is what? E is the identity element. So, these are the four properties that the set H should be satisfied with respect to the binary operation star here. Now, let us see some of its examples. Examples on subgroups. So, here I have written Q plus is a subgroup of R plus. Here Q is what? Q is a set of rational numbers and R is the set of real numbers. We know that set of rational numbers is a subset of real numbers, right? And I know that the set of rational numbers with respect to addition always forms what? Group. So, this is a subset of R and it is also forming a group itself. That is why I can say that Q plus is a subgroup of R plus. Moving into the second example, that is the set of non-zero real numbers with respect to addition is a subgroup of non-zero complex numbers with respect to multiplication. Now see here, we know that this set of non-zero real numbers is a subset of non-zero complex numbers because complex numbers contains real numbers, and I also know that the set of real numbers with respect to multiplication is what? Is forming a group. So both of my properties are satisfied here. It is a subset of C plus C star and it is itself forming what? A group. Therefore, I can say that R star dot is a subgroup of C star dot. Moving into the last example, that is the set of integers with respect to addition. It is a subgroup of set of rational numbers with respect to addition, set of real numbers with respect to addition, and set of complex numbers with respect to addition. We know that this set of integers is a subset of rational numbers, set of integers is a subset of real numbers too, it is a subset of what? Complex numbers too, and it itself is forming what? Group. So I can say that Z plus is a subgroup of Q plus, Z plus is a subgroup of R plus, and similarly for the complex numbers with respect to addition. So students, that's all for today. I hope the session was fruitful to you. Thanks for listening.